It's March and it's Brain Injury Awareness Month, and today we're going to talk about the physiology of concussion. When most people think about concussion, people think about what they see in this GIF over here, where someone hits the front of their head, the brain reverberates and slams into the back of the skull, and people used to think that there's like a bruising situation that happens to the brain. But the most interesting thing that's likely happening is that in the middle parts of the brain itself, there's a shearing force that it actually injures some of those axons deep inside the brain. When your brain first takes the insult at the cellular level, the neurons, some of them may start to die, but at another level, you have some of the neurons become dysfunctional because neurotransmitters like glutamate, which is excitatory, starts to spread throughout the brain and starts to create hyperactivation of different brain regions. Now, this hyperexcitability means that there's more demand for energy because the ions that help to keep the electrical balance in the brain need to get back to equilibrium, and it takes a lot of energy to restore that equilibrium. This creates something called an energy crisis. At the very same time, the blood flow that's going into the brain is actually going to slow down because your body actually creates something called vasoconstriction, in which the arteries get smaller and it's harder for blood to get up there. So you have this energy mismatch situation in which your brain is demanding more energy, but the actual fuel source that's actually trying to get up to the brain cannot get there because the blood flow is inhibited. On top of that, you have other situations where you have calcium that leaks out and it goes into the mitochondria, which are your cell's powerhouses, and it creates mitochondrial dysfunction. So you create this metabolic crisis that is happening inside of the brain on top of all the actual structural damage. To recover from this energetic mismatch can take right around 7 to 10 days when you look at some of the evidence that's out there. So this is a chart where you can see that you have a lot of these neurotransmitters and ions, and you can see that their levels are spiking around 3 to 4 days, and then they'll start to come back to normal within that time frame. But you can see that that line that tracks cerebral blood flow, it stays decreased for up to 7 to 10 days, which is when you would expect that energetic mismatch to resolve. So in theory, between 7 and 10 days, you expect the blood flow to be restored back to normal to match the brain's energy demands. But the truth is, we don't really know if that's the right time frame for every patient, because for patients that play contact sports, they may not be ready to play and get back into their activities, or even people that play really energetically demanding sports, their brain may not be ready to go through exertion again. And that's where there's a graded return to play type of protocol for most sports these days. Generally, we say give patients about 15 to 30 days to get a recovery. And this includes getting appropriate rehab, including aerobic exercise, cervical treatment, and vestibular treatment.